Hi, and welcome to 10.5a Electric Fields 1. In this worksheet, we're going to calculate the strength of the electric fields. How intense is the electric field at specific points in space? What's the electric field intensity? In 10.5b, we draw and we look at diagrams of the electric field lines, which I think is somewhat easier. If you kind of have an artsy mind, you might be able to visualize what the fields look like a little bit easier. If you're more math-minded, you might find this to be a little bit easier. So there is an equation. The equation looks like force divided by at the position in the field. And we're also going to derive another equation for this, KQ over R squared, which I think is a little bit easier to conceptually understand than this one. All right, so let's think about this. If we have a negatively charged sphere, we have this electric field around it. And where do you think the field is going to be strongest? All right, so the sphere is the source. We use a capital Q for the source charge. Where do you think the sphere is going to be strongest? It's going to be where you're closer, right? The closer you get to the sphere, the stronger the field is going to be. So the smaller the distance between you and the sphere, the greater the field. So it's an inverse relationship. Not only inverse, but it's an inverse square relationship, just like the Coulomb's law electrostatic force. The smaller the distance, the greater the field. It's like an opposite inverse relationship. What's another way we could increase this electrostatic field, this electric field? Well, what happens if we make this super negative? All right, what if we increase the charge? How's that going to affect the electric field? Well, if the source charge increases, the field strength should also increase. And that's what this is showing. There's a direct relationship between the source charge and the field. So I think, especially since we've already talked about Coulomb's law, I think this version of the formula should make more sense. By the way, this is just the electrostatic constant, right? So we're just saying that the field strength is directly proportional to the source charge, the thing creating the field, and it's inversely proportional to the distance. The further away you get, the weaker the field is going to be. But that's not what they tell you in the New York State reference table. They tell you this version of the formula, which tells you the amount of force you feel per coulomb of charge at that position in the field. So let's kind of draw this situation. So we have some kind of source charge Q. All right, and this is the thing creating the field. And around this, there's going to be an electric field. And I kind of like to visualize the electric field not with these field lines, which are great. I mean, you could draw the electric field lines and represent it like this, but it's only a two-dimensional representation. And a lot of times it's tempting to think that you only feel the force if you're on this line, right? That's where the electric field is. The electric field isn't at this position. You have to be over here. It's the strongest where this line is. That's not true, all right? I could have drawn a lot more lines. You could draw an infinite amount of lines to represent the field. But that's not how I like to visualize. If I'm thinking conceptually, that's not how I visualize the field. Because it's in 3 dimensions. It's not this 2-dimensional thing. So we want to think about in 3 dimensions. I kind of like to visualize the electric field as like a glowing light. And the closer you are to the object, the stronger the light is going to be. So let's see if I can represent that with a highlighter. So this negative source charge is creating an electric field around it. I've visualized negative is blue, so it's a blue light. And it's kind of weak as the further away you get, but the closer you get, the stronger the field is going to be. And there's you could still kind of see a separation here. That's just because I couldn't smoothly draw that field, but I visualize it as like a smooth transition, and it's getting brighter and brighter the closer you get, because it's getting stronger and stronger, right? So the electric field gets stronger with the square of the distance between the two. And what we're saying is that this is equal to the strength of the field is equal to K times Q over R squared. and it determines what this position is that you're placing, right? So it's just a position, it's a region in the field, and the closer your region is, the stronger it's going to be. That's this relationship. And then the stronger your source charge is going to be, the stronger the electric field intensity is going to be. But there's a different way to think about this, right? So we have this formula here. We have E is equal to Fe over lowercase q. Lowercase q is just a test charge. And that means that you're in this position in the field, you're placing a small positive test charge in order to see how strong the field is at that position. So how many newtons of force would you feel if you placed a positive test charge at this position here? All right, the stronger or I should say the greater this charge is, the more force you feel, right? So it's kind of like Coulomb's law again. Fe is equal to K Q1 Q2 over R squared. There's two charges here, not only the source charge, but the test charge. So let's see, let's put this. So the way we measure the electric field strength is just saying how many newtons of force am I feeling per coulomb of charge that I put there. So for example, if the electric field strength at this location we said was positive 22 newtons per coulomb, all right, well then actually it would be a negative 22, right? Because we put a positive test charge there. This means for every 1 coulomb of charge, I feel 22 newtons of force. So I feel this. It's 22 newtons if this is positive 1 coulombs. However, if this was 2 coulombs of charge, then it would be a 2 down there. In order for the field strength to remain the same, I would have to make this 44. So this would be 44 newtons of charge. So it's a little bit, it's kind of like a little bit hard to explain. It's not as easily explainable as this formula here. It's basically telling you how many newtons of force per coulomb of charge at a specific location in the field. And if you're wondering where this equation comes from, let's derive it really quickly and then we could do the problems. So we know that Fe is equal to K Q1 Q2 over R squared. But in this case, instead of Q1 and Q2, we're using capital Q and Q naught, which is a test charge. And Q naught is always positive. It's a convention thing. Why is it positive? Because now if we have a negative source charge and we have a positive test charge, we could say, okay, positive is attracted to negative. The electric field is going to be attractive. And we could draw the electric field lines and everybody's going to know, okay, I'm drawing the electric field lines going into this object. I know that object is going to be negative because only a positive thing would go in there. However, if you made this a negative test charge, then the negative test charge wouldn't be attracted to this negative object. And you'd have to draw so this is now a negative charge. Negative is repelled by negative. And you would have a completely different looking electric field line than everybody else. That's not the convention. The convention is to use a positive test charge. And that's wrong. The negative sign, that's wrong. We want to use a positive test charge always when we're talking about the direction of the electric field. Just because that's the convention, that's what everybody has agreed to. So it's a positive test charge. So if you saw the lines going in, the field is going in this way. We're talking about this more in the next video. The positive test charge thing. But let's keep going with this. So E is equal to Fe over Q, right? So then this is the test charge. So let's plug in what we know over here. So E is equal to K Q times Q over R squared. That's Fe. But we still have this divided by Q naught thing. divided by Q naught. So now we want to simplify this, obviously. It's an improper fraction. You could do the keep, change, flip again. So E is equal to keep K, Q naught over R squared. Change this, and then flip this. So this is 1 over Q naught. And as you could see, the Q naughts cancel out, leaving you with K, Q over R squared. And again, this capital Q is the source charge. It's the thing creating the field. So it's this negative charge shown here. This is capital Q. All right. And again, I think it's easier to conceptualize. The stronger the source charge, the stronger the field is going to be. The further away you get, so if this is R and now this is a greater R than this, so as R increases, the field decreases. So this is a strong field, this is a weak field. This is a small r, this is a great R. It's an inverse relationship, inverse square relationship. All right, let's do some problems. An object with a net charge of 4.8 times 10 to the negative 6 coulombs experience an electrostatic force having a magnitude of 6 times 10 to the negative 2 newtons when placed near a negatively charged metal sphere. So we don't know what the source charge is, we just know it's negative, but we don't know the magnitude. What is the electric field strength at this location? So you have this negative charge, you have this positive 4.8 times 10 to the negative 6 coulombs there, and we want to know at this position in space, how strong is the electric field? How many newtons would you feel for every 1 coulomb of charge that you place here? All right, we already know what the force felt by this one specific charge is, but what is the field strength? How many newtons per coulomb? So E is equal to Fe over Q. E is equal to 6 times 10 to the negative 2 newtons divided by 4.8 times 10 to the negative 6 coulombs, and you get 1.25 times 10 to the 4 newtons per coulomb. So that's pretty strong. You feel 1,000 or 12,500 newtons for every 1 coulomb of charge that you place there. So if you put 1 coulomb here, you'd feel 12,500 newtons for every coulomb. Now the signs on this is a little bit deceiving because it says it's a magnitude of this many newtons. So they're not telling you the direction, they're just telling you the magnitude. Let's try to figure out what the direction should be really quick, just so that we're pretty thorough. If this is a negatively charged sphere, as it says, and we're assuming that they're telling us this is a positive coulombs, all right, it should be attractive, right? The positive 4.8 microcoulombs is attracted to this negative sphere. And we said that if it's attractive, the force is negative. So even though they're saying the magnitude is this, well, the direction is negative. And when we plug this in here, we get a negative number for our field strength, which shows it's attractive, which is what our field lines look like that I drew right here. All right. Again, we'll talk about the direction of the field a little bit more, I think, in the next problem, in the next video. So number 2 says, what is the magnitude of the electric field intensity? So they're looking for E. At a point where a proton, don't forget, it's a proton. Now, what's the charge of a proton? It's 1.6 times 10 to the negative 19 coulombs. Positive. That's the E, the elementary charge that you found on the front of your reference table. So if it says it's a proton, that's a key word. It's like hidden information, just like we did in the mechanics. When it says at rest, your velocity is 0 meters per second. If it tells you a proton, your charge is this. If it tells you an electron, your charge is negative that. So that's important. It says an electrostatic force, so Fe is 2.3 times 10 to the negative 25th newtons. So the electric field strength is equal to the amount of force you feel per unit charge. So you get 2.3 times 10 to the negative 25th divided by 1.6 times 10 to the negative 19. And that's a Newton, that's a Coulomb. That's how we get an answer in terms of newtons per Coulomb. And you get 1.4 times 10 to the negative 6 newtons per Coulomb of charge at that position in the field. Okay. So what would you expect that source charge to be? If this is the source charge, and here's our positive charge, and I'm feeling a positive force, and a positive, the electric field direction is positive, the force is repulsive, because it's positive, so Fe is going this way. This should be a positive source charge. And, yep, that's a positive number, so we draw where a positive test charge would go. It would go away from the object like this. This is the electric field lines for that object. At this position in the field, the strength is 1.4 times 10 to the negative 6 newtons for every 1 Coulomb of charge that you place there. All right, that's what that means. How strong is the field at that point? It's not necessarily dependent on how much charge you place there. It's just saying what's the strength of the field itself at that position. It says, what is the magnitude of the electrostatic force acting on an electron? So Q is equal to negative 1.6 times 10 to the negative 19 coulombs in an electric field having a strength of 5 times 10 to the third newtons per coulomb. So what's the electrostatic force? So to Fe over Q. 5 times 10 to the third is equal to Fe over 1.6 times 10 to the negative 19. And the electrostatic force that you feel is 8 times 10 to the negative 16 newtons. Okay. Number 4. Okay, so let's see what this means. This is positive, and this is negative, actually. So this is a negative number. And at this position in the field, they're telling you the field strength is 5,000 newtons per coulomb. So if you put 1 coulomb here, then you would feel 5,000 newtons positive in this direction. 5,000 newtons for every 1 coulomb of charge that you place in that position. But we're not placing 1 coulomb of charge there. That is a pretty big amount of coulombs. What we're doing is we're placing 1 electron there. So we're not going to feel 5,000 newtons. We only feel 8 times 10 to the negative 16 newtons. But the strength of the field is still 5,000 newtons per coulomb at this particular position. The amount of force you feel just depends on how much charge you're placing at that point. Again, if you place 1 coulomb of charge there, you'll feel the 5,000 newtons. If you put 2 coulombs of charge there, you'll feel more. You'll feel 10,000 newtons. But in this case, it's just 1 electron, so it's a tiny amount of newtons. All right, because 1 electron is not even close to 1 coulomb of charge. It's 10 to the negative 19 coulombs. 1.6, there you go. Number 4, a particle experiences an electrostatic force of 5.5 times 10 to the negative 11 newtons at a point where an electric field, where the electric field intensity is 3 times 10 to the third newtons per coulomb. What is the charge of the particle? So you use your formula. The strength of the field is 3,000 newtons for every coulomb that you place there. But you don't feel 3,000, you feel 5.5 times 10 to the negative 11 newtons. So you're definitely not putting 1 coulomb there, because that's a tiny number. You're putting a lot less than 1 coulomb. So what's Q? How much charge is being placed there? So you do 5.5 times 10 to the negative 11 divided by 3,000. And you get 1.83 times 10 to the negative 14 coulombs of charge at that point. Yep, and everything's positive. So yeah, you have an electric field that's being repulsive. If you place a positive charge there, it's going to repel, and you're feeling a repulsive force. Fe is also positive. So that's the idea there. At point P in an electric field, the magnitude of the electrostatic force on a proton is 4 times 10 to the negative 10 newtons. So it's a proton, you know the charge. Negative 19 coulombs. And you know the force. It says, what is the magnitude of the electric field intensity? E is equal to Fe over Q. E is equal to 4 times 10 to the negative 10 over 1.6 times 10 to the negative 19 newtons per coulomb. And you get 2.5 times 10 to the 9 newtons per coulomb. So for every coulomb of charge there, you're getting this many newtons of force. But the reason you're getting a lot smaller amount of force is you're not putting 1 coulomb there. You're putting a tiny amount of coulombs at that position. So again, the electric field strength is just telling you, it's a way to measure how strong the field is, how much force is being exerted at that point for every coulomb that you put there. Because the amount of force changes depending on how much coulombs are there, right? So this is just a way to say how much force per charge. So the gravitational field strength, which is little g, is 2 newtons per kilogram, as electric field strength is 2 newtons per coulomb. That's about it. Have a good day.